Title of my talk is A Fundamental Connection Between Quantum Theory and Indivisible Stochastic Processes. There's going to be a lot of content in this talk. Just warning you, there's going to be a lot happening here. This is a very comprehensive reformulation of a lot of old ideas. I would argue of many calcified ideas, and the problem when you have a lot of calcification is you have to work pretty hard to uncalcify before you can start doing something new. This talk is based on several papers on the archive for the philosophers among you. Papers are also on the PhilSci archive, and there's a few more papers on the way in draft stage right now. So I'm going to get started. I'll explain this picture in a little bit. Y'all know this picture? This is René Magritte's Ceci n'est pas une pipe. It's French for this is not a pipe. And you look at the picture and you go, well, I mean, it's pipe. And what Magritte said is, oh, it is. It's a pipe, is it? Can you smoke it? The answer, of course, you can't. And it's supposed to be a statement about the difference between a thing and the representation of a thing. This is the representation of a pipe, not the pipe itself. And you can see that I've artfully placed it in bracket notation for reasons that will become clear in a little bit. Okay. All right, what are the goals of this talk? Right. The goals of this talk. The main goal of the talk is to argue that every quantum system can be understood as an indivisible stochastic process in disguise. It's indivisible in quotation marks. There are some additional goals as well. First of all, I need to define what an indivisible stochastic process is. I'll do that in a moment. I'm also going to give a correspondence between indivisible stochastic processes as a theory and quantum theory, with hopefully applications in all kinds of ways, most obviously to stochastic modeling. I'm also going to describe some concrete examples, including a classical analog model of a qubit. These are models that may be helpful for understanding how an indivisible stochastic process works, for understanding this connection between these models and quantum theory. But arguably, some of them may be realizable in numerical simulations or ideally in the lab. That would be very interesting. Some of you may know that there are analog models of like black holes, fluid systems, where you take the Navier-Stokes equations, the partial differential equations to describe fluids, and with a couple of clever mathematical transformations, you can make them look just like the equations that describe the space-time of a black hole. And the idea is that by studying these fluid systems in a laboratory, you may be able to actually learn things about black holes. These are called classical analog models. And the idea here is you could have a classical analog model of a qubit and maybe of other systems. I also am, my plans are to demystify and deflate some of the exotic features of quantum systems like interference, entanglement, decoherence, and measurements. And the second part of the talk, that's all the first part. I'll go pretty quickly. The second part of the talk is metaphysically ambitious, is to introduce a microphysical definition of causal influences for quantum systems and argue that it is in fact local. Okay, and this is going to require breaking up some, like I said, calcified wisdom, and I'll get to that in a little bit. I'm going to begin with a motivating example. Let's revisit the famous double slit experiment. Now, the new formulation of quantum theory I'm going to be talking about here is not limited to any particular kind of system. It's not limited to systems of particles, but this is, I think, a paradigmatic example. Richard Feynman said this is like the one example that really contains the only mystery in quantum theory. And maybe those are famous last words after this talk. So the double slit experiment, here's what one imagines. One imagines that you send particles one at a time. That's always emphasized, one at a time, right? Because, they want to keep things simple. Right? They don't want to overwhelm you with too many particles, or maybe the particles, if they're sent more than one at a time, they could bump into each other. So really, just for your own good, we're going to send one particle at a time. But don't ask too many questions. We send them one at a time toward a wall with two slits in it, and then we observe where the particle arrives on a screen. And then we repeat this experiment many, many times. We collect where all the particles have landed one at a time, and we build up a histogram instead of data points. Now, this one at a time thing is really a sly move. It's done so that we have a 3D configuration space. Configuration spaces are where the wave functions of quantum mechanics, the position space wave functions, where they live. So some of you learn a little bit of quantum mechanics. Maybe you do quantum mechanics. Maybe you're new to quantum mechanics. I don't know everyone's background here. Can I just ask, how many of you have taken a full 1-year undergraduate course in quantum mechanics? Okay. How many of you have not yet taken a 1-year undergraduate course in quantum mechanics? That's good. Okay. Yeah. I don't know. It's like a high school summer program here at Brown. Is that? Yeah. Okay. Yeah. I've heard it's an amazing program. In fact, I think we stole the director of the program for our summer program. So Brown's got an awesome program. Okay. So you may have heard, or maybe you know that they're like wave functions, right? And particles have wave functions, and the waves are sort of move around in space, and you can think of the particles as waves. That's not actually how things work. Wave functions, at least position space wave functions, the usual ones you hear about, they live in what's called configuration space. The space of all possible positions of where things are. Was known all the way back when Schrodinger introduced wave functions from the beginning. If you've got n particles in 3D, the configuration space is a set of numbers that specify where all the particles are. That's 3n numbers per configuration. And so configuration space for 10 particles is a 30-dimensional space, and that's where the wave functions live. The reason they give you a one particle at a time picture here is that you'll think, oh, one particle that's a 3D configuration space looks like physical 3D space. These are waves moving in 3D space, but that is a lie. And the moment you go to 2 particles, you have 6-dimensional wave functions. Good luck trying to understand how that's supposed to explain the double slit, whatever. I'm belaboring the point. All right, so here's the setup. We send 1 particle at a time toward 2 slits. We'll assume the slits are fairly close together. Let A be a variable that in some general sense labels different possible starting conditions. B, which labels which slit of the 2 slits it goes through, and C, where it lands. There's the 3 variables. Okay, so the usual classical assumption is that we figure out the conditional probability all the way on the right. That's PB, vertical line means given A. That's the conditional probability, the probability that it will go through the Bth slit given whatever the initial conditions are. We take that conditional probability, we multiply it by the conditional probability given that it went through the Bth slit, where C does it land on the screen, and then we sum over the 2 possible slits. And this is supposed to give us the final conditional probability. Conditioned on the initial conditions A, where does it land? The probability where it lands. I'm mentioning probabilities here, but this description also holds if you treat the system deterministically. In that case, the probabilities are just 1s and 0s. So this also captures the idea that we would treat the system like with Newtonian mechanics. And this is just assumed, right? You pick up the first chapter of volume 3 of Feynman's lectures on physics, where he does this example, or really any textbook that does this example. They won't say that they're making this assumption, but they're making this assumption. Why is it an assumption? Because this doesn't actually follow from the general rules of probability or marginalization. It entails an implicit assumption, a Markov or so-called visibility assumption at B, right? If you actually just try to write down what this statement should be, just directly from the laws of probability theory, what you would actually find is that you need to replace that probability P of C given B with P of C given A and B. And then it's actually much more complicated what the answer is going to be. It requires a summation on B and A. The whole thing is just a little more tricky. Okay, but anyway, if you make that assumption, you get the following prediction of the pattern of landing sites over many repetitions, right? These curves here, you don't see a curve on one run of the experiment. The curves are what you get from building up lots and lots of landing sites. Okay, so you get these 2 curves. They merge together over many trials. You get this overall distribution. And in fact, this is indeed what you see. If you do this experiment, little pebbles, you throw pebbles at a wall, like macroscopic objects like stones or pebbles. When you do this with an electron or photon, you do not see that pattern. What you see is this pattern. You look at this, you go, oh my gosh, that's a wave. Quantum mechanics is about waves. Waves in 3D space. Oh my goodness. Okay. But does it really mean the particle is in fact a Schrodinger wave, or that the particle or the wave or whatever goes through both slits? Actually, not necessarily. Not necessarily. I'm going to show in this talk that you can account for this pattern merely by not making that assumption, not assuming that we have this Markov or divisibility assumption in B. By dropping that, we will see that generically you get patterns like that pattern without any assumption of wave behavior. Okay? And that's already a striking fact, and I'm going to show you how it works in just a moment. To start, I'm going to have to tell you what an indivisible stochastic process is.
Before you move on, I have a question.
Yes, please, Kelly.
Why, like, is this assumption ever justified?
I went back.
The visibility assumption in the first place?
Is it justified?
Yeah.
It is absolutely justified. I'm going to justify when it's just. I'm going to. I'm going to explain in what circumstances it's justified. I'm going to explain why we're able to use it and when.
Okay.
But let me just say that broadly speaking, in Newtonian mechanics, it works. In Newtonian mechanics, you can evolve a system from one time to another, look at the state of the system at that later time, and then if you want, the laws are robust enough, comprehensive enough that you could take that later time and then evolve after that, right? This is the divisibility assumption in a deterministic sense. For a probabilistic stochastic system, this would be the Markov assumption, that you can ignore the past, just use the present state of the system, and then the laws, given any time, you take the state of the system at any time, and the laws are robust enough to tell you what will happen probabilistically next. So when you have a deterministic Newtonian type system or a Markov chain, like a Markov chain model, those are cases in which this will happen. The question is, how do we justify why those sorts of models ever work?
Yeah.
And I'm going to get to that in a little bit.
Fantastic. Thank you.
You're welcome. Sorry, it's funny. This button, it feels like one side should be forward and one side backward, but actually both sides are forward. That seems somehow fitting today. Okay, so an indivisible stochastic process, what is it? It's just a simple generalization of a non-Markovian stochastic process. We all know what non-Markovian stochastic processes are. It's trivial. So I really have nothing else to say, right? Okay, no, just joking. Just joking. Just joking. Non-Markovian stochastic processes are the kinds of things that if you pick up a standard textbook on stochastic processes, they'll mention, like in the final chapter in the last paragraph, and they'll say it's beyond the scope of the text, right? And that's actually a shame, because I'm going to argue that we're getting evidence from all kinds of directions that there is something inherently non-Markovian about quantum mechanics. I'm not going to maybe shout out particular names, but there are certain people in this audience who are also working on ways of thinking about quantum mechanics that indicate that there's something deeply non-Markovian going on. We're getting this information from lots of directions. So we have to confront this idea that you could have non-Markovian behavior in a quantum system. And actually, what we want is a particular generalization of a non-Markovian process called an indivisible stochastic process. This is a very recent idea. Okay, I'll mention it in a moment, but this idea is, well, I'm not sure if I have this in my slides. Let me just quickly say, I may have it on a later slide. The idea goes back only to 2006 in a preprint from work on what are called quantum channels. Quantum channels are generalizations of the Schrödinger equation for open quantum systems. There's a paper by Mikhail Wolf and Ignacio Chirac called Dividing Quantum Channels. It's all about how, for a quantum system, evolving with interactions made with its environment, not necessarily according to the Schrödinger equation, some generalization of the Schrödinger equation, there can be a failure of iterativeness of evolution. You can't just evolve the system and you have the laws that tell you how to evolve it in steps. You may only be able to evolve it in one giant leap. Right? That's this idea. The idea that you could take this indivisibility notion and extend it to the classical case shows up in 2020. That's the first place anyone ever wrote it down, and it was in a figure, like an offhand throwaway statement in some figure in a review article, like on page 15 of some 80-page review article. This is an incredibly new idea, which is surprising because it's actually a very simple idea. So what is an indivisible stochastic process? Well, it consists of some fixed ingredients. These are the ingredients of the model that will be the same every time you run the system. One ingredient is the configuration space, or the sample space, the set of possible ways the system can be, the configurations. If you want to keep a concrete picture in your head, and we'll have some concrete models in a moment, think of a system of 7 particles. The configurations are all the arrangements the particles can be in space. Okay. And then for times t and t prime, in respective index sets, script t prime, index set just means a collection of all the allowed, the available values of t and t prime. A first order conditional probability map, that's the Greek letter gamma. It's a map from t naught to t. It takes in 2 configurations, a configuration at t naught, that's what we're conditioning on. It's called first order because we're conditioning on just one configuration. And then another configuration at t, and the result is the conditional probability that the system will be in t, given that it was in a particular configuration at t naught. And that probability is going to be a probability, it's going to be a number in the closed interval from 0 to 1. Then we have some contingent ingredients. These are things that may vary from run to run. And for times t in that first index set, some probability distribution, p of t, right? That takes in a configuration, a question, like which configuration is this at time t, and spits out the probability that it is in fact in that configuration at time t. And this can vary from run to run. You may get a different behavior of the probability distribution. That's it. That's the whole model. It's actually pretty simple. It's simpler looking than even a Newtonian system. Very simple, but again, never written down until like, and in fact, even when it was mentioned in that paper, it wasn't like laid out. It was just a throwaway comment, right? This is like, I think this definition has not actually been like written down in literature before. Let me say a little bit more about indivisibility, okay? So again, it's a simple and remarkably new idea, relatively recent vintage. It's a failure of iterativeness. It's so new that I didn't know that it existed. And I noticed it coming out of the work I was doing, and I was looking for a name for it. I didn't want to call it irreducible because God knows that's been used too much in math and physics. And I was looking for a name, and I decided, well, indivisible sounds like a good name. And then I looked around, and in fact, just like 2 years earlier, it had been introduced and called I guess in the quantum channels literature, went back to that 2008. But the fact that like it was so new that I'd never even heard of it, and I picked the name that in fact was the name that had already been given to it is kind of remarkable. Okay, so I said a little bit of the history before. What is indivisibility? Well, I didn't make any strong conditions on this map, gamma, right? So in general, it will fail to have this divisibility property. Let me see what's going on here. If you give me 3 times t naught, t prime in the middle, and then another time t, you might wonder, will I have first order conditional maps that take me from t naught to t prime and then from t prime to t and give me the same answer as the true correct map that takes me from t naught all the way to t in one loop? And the answer is generically no. Generically, this purple map in the middle simply will not be in the laws. It won't be part of the model. And so you simply won't be able to divide the evolution up into subintervals of time. Now, this isn't actually a very new idea. This also is true for non-Markovian processes like you find in the textbooks. But these models have way less structure than non-Markovian models. Unlike for textbook non-Markovian stochastic processes, I will not be specifying any higher order conditional probabilities. So an implicit assumption that one makes when working with a textbook non-Markovian stochastic process is that in addition to these first order conditional probabilities, you condition on one configuration, and then you get the probability of some other configuration some other time. Usually you assume like a whole tower of higher order conditional probabilities. You can condition on 2 or 3 or 7 or a million configurations, and then get the probability that the system will be in some collection of later configurations. Usually these are assumed to be specified in the non-Markovian model. They won't be specified here. And in particular, what this means is that an indivisible stochastic process may agree with a large, maybe infinite number of textbook non-Markovian processes. That is, there may be many different towers of higher order conditional probabilities that agree with the more minimal sparse set of conditional probabilities that define this model. So this is a strict generalization of those models. Okay, I'm now going to give a concrete example of an indivisible stochastic system, indivisible stochastic process, and also take the opportunity to show where quantum theory shows up in this picture. So consider the simplest kind of discrete time deterministic process, right? This is a process in which there are n configurations, and they deterministically transition in time steps. So time step delta t, the system transitions from configuration 1, let's just say to 7, and then the next time step to 3, and then to 2, and then to 13, and then to 5, and so on and so on and so on, until eventually 4 and then 1, right? If it's a finite number of configurations, and this is a deterministic reversible permutation map, it has to eventually come back to where it started. It's called a recurrence, and then it will just repeat. So super simple deterministic system. Well, now a little bit of math. Sigma here is a permutation matrix. It's a set of zeros and ones. Basically, it's the identity matrix, the n by identity matrix, with some of the rows permuted. And this encodes what steps are taken as the system evolves. Well, every permutation matrix is in particular a unitary matrix. A unitary matrix is a matrix whose adjoint, or it's real, so just as transpose, is the inverse matrix. And unitary matrices have a number of beautiful properties. For t, any smoothly variable time, I can set sigma to the power t over delta t. That's like, in general, an irrational power, but you can do that with a unitary matrix. And the result defines a new unitary matrix U. I'm saying U from 0 to t, because in a moment we're going to see that this takes us from time 0 to time t. This matrix exists and is still unitary. That's a property the unitary matrices have. You can take their powers. So what I'm going to do now is take the ijth entry of that matrix. That's the ijth entry. It's in general going to be a complex number. When you do this, in general, you get a complex number when you take this power. And I'm going to absolute value square that entry. What I get is a manifestly non-negative quantity, gamma ij. And remarkably, gamma ij is a matrix, n by n matrix with non-negative entries. Its columns sum to 1, so it's called a stochastic matrix, and it has an interpretation as describing first-order transition probabilities. Actually, in this case, it's not just stochastic, it's unistochastic, which is just a fancy way of saying that its entries are the mod squares of the entries of unitary. And that gives it a whole bunch of cool additional properties. One thing, it guarantees that the rows also sum to 1, which is makes it called doubly stochastic.
Sorry,
Yes.
really dumb question. Why is the column summing to 1 makes it stochastic? Should
The
that
definition of a stochastic matrix is a square matrix with non-negative entries whose columns sum to 1.
Okay.
Yeah. Now, some people who work in stochastic processes like using row stochastic matrices instead, but nobody's perfect.
Okay.
So, yeah.
So why that definition? Because when I think stochastic process, I think something that does not depend on whose evolution is not only depends on the previous step.
So what you're pointing out is a Markov matrix. That's a
Ah.
special kind of stochastic matrix.
Okay.
And one of the things, so there's tremendous amount of, and it's not anyone's fault, but a tremendous amount of tunnel vision, because people use terms like stochastic and Markov interchangeably.
Right.
They're not interchangeable. You need to just throw all that away, and we're going to be just very clear. This is definitely not a Markov process.
Right.
In fact, this describes an indivisible stochastic process. You can check that for arbitrary times, you won't be able to divide the dynamics.
Mhm.
However, it does describe an indivisible stochastic process along the lines of the basic definition I gave before, and it beautifully, smoothly, analytically interpolates the original discrete process, in the sense that if you plug in any discrete number of time steps, so if I plug in as my final time tn, an integer number of time steps, it just turns back into n applications of the permutation matrix, right? So it replicates the behavior of the discrete deterministic system at the discrete times, but it also lets you talk about what's happening between the discrete times. And this is going to get even more weird and bizarre in a moment, okay? So let me just quickly say, you can use the unitary matrix that we defined, right? This matrix that we got out of, backwards, okay. Right, we defined this unitary matrix to be this power of sigma. You can use that unitary matrix, and you can do a little bit of manipulations. You can define a new matrix. You take the original matrix from 0 to t. You take the original matrix from 0 to another time t prime, take its adjoint, multiply them together, and this defines a new, still unitary matrix that I'll call U of t prime from t. And I'm going to call it that because these three matrices now satisfy this beautiful composition law, right? The first matrix takes you from 0 to t prime, the next from t prime to t, and the answer agrees with the giant leap from 0 to t. You might go, wait a second, I just said this was indivisible. It is. This unitary representation lets you pretend it's divisible, right? It has this nice composition law, but this is actually not telling you the underlying process is divisible. In fact, you can check that we still fail to have this purple matrix in between for the original stochastic matrix for this process. And actually, if you try to take the U that we introduced in the top line, it's a unitary, it goes from t prime to t. What if I just square its entries and use that to define, just by hand, a gamma that goes from t prime to t? You'll find that it just fails to give you the divisibility you want. And interestingly, if you compute the discrepancy between the true giant leap evolution and the nearest approximate divisible evolution, not only is the answer non-zero, but the answer is mathematically identical to the terms you get in quantum mechanical interference, which is already a sign that you get interference effects generically from these kinds of systems without any mention of waves. When I say that it replicates them exactly, I mean literally the formula for quantum mechanical interference is the formula you get here. It's the same formula. However, in this case, it's not a completely indivisible process. It will in fact divide at the special discrete time steps. You can show that at the discrete time steps, you can in fact write down a new map that will take you to the next time step. So this is a process that's indivisible for most times, except at the discrete time step times. And those special times where it is divisible are naturally called division events, and those will play a prominent role in the work ahead. Okay? So that's our first example of the system. But notice something. U here is a smooth function of t. I define it to be this rational power of a permutation matrix, perfectly smooth. I can take its derivatives. So I can define a new matrix H by taking the derivative of U, multiplying by U dagger, and introducing a complex number I, and for units, a quantity H bar. It's not necessarily the H bar, but it's just a quantity that has the right units that will make H have units of energy, which is convenient for all sorts of purposes. This is by construction self-adjoint. You can check this definition as self-adjoint. The I is crucial for that. Once we have this H, we can also take the initial probability distribution. So if I didn't know which configuration my discrete system started in, it has some initial probabilities at time 0. I can line those up on the diagonal of a square matrix with otherwise zeros everywhere else. I can sandwich that diagonal matrix of initial probabilities between U and U dagger and define a time-dependent matrix rho. And then this matrix rho will evolve according to the von Neumann equation. This von Neumann equation is a generalization of the Schrodinger equation. Schrodinger equation is a special case. So this is an emergent quantum dynamics. This is a system that was the simplest, discrete, deterministic, couldn't be more classical looking. And under the hood is a quantum system with a Hamiltonian and energy eigenvalues and a Schrodinger equation, which is a special case of the von Neumann equation. Those brackets there on the right-hand side, that's a commutator. That's H times rho minus rho times H. It's an actual commutator of non-commuting, non-diagonal matrices. Rho is, by the way, called the density matrix. It's a generalization of the wave functions or state vectors that one finds in quantum mechanics. That's very interesting. Very interesting. Let's do another model, another concrete model. This one's going to be a little bit different. This is going to be a discrete model of a qubit. So consider the following setup. We've got a black box. I mean, not literally like it's a black box. I just mean that you don't know what's inside of it. I mean, you know what could be inside of it, but you don't know for a fact what is inside of it. Yeah, but it could contain, either of two possible classical systems, A and B, and we'll assume we've coarse-grained our description so that A and B each have two possible configurations. Think of coins, right? A and B are coins, heads or tails. We're just coarse-graining our description so there's basically two configurations. And A and B have two configurations, 1 and 2, and we'll assume that 1 looks pretty similar for A and B, and 2 looks pretty similar. Again, think of two coins, where the ones where the heads, right, both coins, those clearly correspond, and tails clearly correspond, even if the coins aren't exactly the same. For the first system, let's assign the two configurations energies, E1 and E2, and let's assume E1 is the ground state, E1 is the lower energy state. For the other system, we're going to reverse it. E2 will be the ground state, E1 will be the excited state, but we'll assume the spacing between the energies is the same for both systems. So basically, there's a symmetry, right? E1 and E2 for the first system, that flips for the second system. Okay. That's a little weird. It's simple, but weird. And this weirdness is, I think, why no one's written down this model before. But it's not that strange. It's not impossible to implement this. It's just, why would you do it? Well, we'll explain in a moment why I'm doing it. Now to do is thermally couple this black box to a reservoir. That just means I put it into thermal contact with some big system with a well-defined temperature. And, there's now thermodynamics. Hopefully people have, some of you have seen some thermodynamics. That we expect that this system will come to thermal equilibrium and will also gradually develop the same temperature. And then we imagine that we can control the temperature of the reservoir gradually so that everything stays near equilibrium during this process. So the temperature is now going to be a choice up to us, a function of the time t, smooth, gradually changing function of the time t. We will assume that at the initial time 0, we will assume that the temperature starts at 0. Now, the way that thermodynamics works is at 0 temperature, the system is definitely in its ground state. As you vary the temperature, what temperatures are really doing is changing the probability that the system is in its various energy eigenstates. When you turn your oven on at a high temperature, what you're doing is increasing the probabilities associated with the higher energy states of your system. And there's a precise formula for how that works at thermal equilibrium, the Boltzmann distribution. I won't need those details. Let me just say that when you set this up, what you'll find is that there are 4 Boltzmann occupation probabilities. Why 4? Because the system could, at the later time t in question, be in either of its two configurations, 1 or 2. But there's also some conditional dependence on where the system began. If in the box you had system A, then the system began in configuration 1, because that was the ground state, and that's the state the system will be in at zero temperature. If instead in the box you had system B, then it will initially be in state 2 because that's that system's ground state. So there are in fact 4 conditional probabilities here. Which configuration the system is at a time t, conditioned on which configuration the system was in at time 0. And these naturally form a 2x2 stochastic matrix. Non-negative probability entries, columns sum to 1 because each column is in fact a probability distribution. By the symmetry of how this problem was defined, the diagonal entries of this matrix are the same. Because just interchange system 1 and 2, you get the same looking picture. And the off-diagonal entries will also have to be the same. In fact, they have to be 1 minus the on-diagonal entries. So this is not just any stochastic matrix, it's a doubly stochastic matrix. So gamma is a 2x2 doubly stochastic matrix, and all 2x2 doubly stochastic matrices, 2x2, this doesn't hold beyond 2x2, but all 2x2 doubly stochastic matrices are unistochastic. That means there exists a 2x2 unitary matrix U, such that when you square its individual entries, you get the entries of the stochastic matrix, just like we saw in the previous example. And this means you're going to get the emergent quantum picture. It's going to be, if everything is smooth enough, you're going to get Hamiltonian, you're going to get a von Neumann equation, Schrödinger equation, the whole story. The original stochastic description we began with will generically be indivisible. That gamma, there was no condition we placed on it had to be divisible, and generically it will not be divisible. In fact, because we can control the temperature function, we can make those conditional probabilities whatever we want. And there's some very simple, perfectly smooth analytic choices like e to the minus t squared over tau squared for a constant tau, for which you can just provably check that the system will generically be indivisible. Right? Of course, the unitary description still has the composition property, just like we saw for the other system. When you work with the unitary picture, with U, you get what looks like divisibility. Right? So the unitary description is quite useful. It gives us this convenient divisible looking formalism, but there's a cost. The cost is that that matrix rho that contained our probabilities, the density matrix, will, as time progresses, develop these weird off-diagonal entries called coherences. It turns out coherences are superposition of wave functions. What we call superposition of wave functions when expressed in density matrix formalism are just those off-diagonal entries. So this is ultimately the emergence of superposition as well. Okay? But now we have a better understanding of what's going on. They're the price we had to pay to get what looks like a divisible description. You can't just get a divisible description for free. Nothing in life is free. Sorry. If you want a divisible description, you have to pay the cost somewhere. And the cost is, instead of working with a nice simple probability distribution, you now have to encode your probabilities into this n by n matrix with off-diagonal entries. Those off-diagonal entries are artifacts of the underlying indivisibility of the true process. They're not exotic, they're not mysterious, they're not, oh, the cat's alive and dead. They're just artifacts of this particular description, which is convenient in many ways, but secretly encodes the indivisibility of the underlying process. Okay, let's get back to interference for a second. So consider what you in quantum mechanics would call amplitudes. Amplitudes for two processes. Two processes that begin with the same initial condition, 1. I'm using blue here for initial conditions, red for final conditions, just public color coding. And end in configuration 2. Okay, and in the first path or amplitude, at the intermediate time t prime in question, we're going to say that the system is in configuration 1. In the second, we're going to say the system is in configuration 2. When you pick up a book on quantum mechanics, they'll say, oh, the system can go on all these paths. It can take a path that goes 1, 1, 2, or 1, 2, 2, right? And we assign these complex numbers. This is linear algebra. What we're doing here is we are taking a vector 1 that represents the first configuration, multiplying by the matrix U, and then multiplying by the row vector corresponding to 1. Then we take the column vector again with 1, we multiply by the next matrix U, and then multiply by the row vector representing 2. And this will give us in general some complex number. And then we do it for path, that should say path 2, sorry, it's typo, path 1 and path 2. Well, it's easy to show that if you add these complex numbers together, then take the absolute value square of that resulting complex number, you will get the correct probability for the answer, right? This is called a coherent sum. However, if you think that these paths are like truly happening and we can treat them as things you square and get probabilities from, and you square them first and then add them together, you get the wrong answer. And this is another way to talk about interference. And we hope people say, oh, this means the system is taking all paths at once and you have to add the paths together. And then no, it's just that the system is indivisible. And if you pretend it's divisible and pretend that you can assign these, amplitudes and probabilities to individual paths, you just get the wrong answer. And the fact that the system is indivisible is encoded in the failure of this naive, square first and then add. Well, this is exactly probabilistic interference, and it's showing up in a completely classical model of the qubit. And as far as I can tell, this is one of the first examples of probabilistic interference, not some hackneyed analogy to like electromagnetic wave interference. This is like probability interference. Different possibilities with a probabilistic meaning interfering with each other in a completely classical system. Okay. So I've given some examples. You've seen quantum theory emerge in these examples. Now, with that as motivation, let's set up the correspondence.
Before you move on,
Yes, please.
question, I may be like focusing on the wrong thing, but the example motive, like when their physical setup, I'm just trying to understand. So the configurations look the same, but they have different energies for system B and system A.
Yes.
And so, can you explain? I guess, like how would that work?
So they obviously can't be exactly the same.
Okay.
But imagine you've got two coins that look pretty much the same.
Okay.
But like one of them is a little magnetized and the other is magnetized in the other way.
Okay.
And so one of them is in the ground state with its heads and the other is in
Yeah,
its
I
ground
see.
state with its tails. That's basically what I
Okay,
mean.
thank you. That's helpful.
Good. Okay. Good question. Okay, so let's now talk about this more general correspondence. We've already begun to see some examples of it. First, let's talk about the stochastic to quantum direction. Start with the indivisible stochastic process. Given any indivisible stochastic process with n configurations, and I'll be assuming the discrete case, you can generalize this to continuous configuration spaces. Then you have to integrals and measures, and it gets sort of annoying. Introduce a, in general, not unique, n by n matrix theta, according to the following recipe. Essentially, what we're doing here is we're taking the fact that each entry of gamma being a probability is non-negative, and we're solving that condition by working in terms of this other matrix theta, which in general will be allowed to have complex numbers in it. Theta here is playing the role of u, except that I'm not assuming that it's unitary. There's no assumption here that this is unitary, but I can always do this. Theta is not unique. However, because the columns of gamma have to sum to 1 because they describe probabilities, we get the following condition on theta. You can think of this as a very weak generalization of the unitarity condition of the unitary matrix. Now, if gamma, our original matrix, happened to be unistochastic, as it was in the examples we saw before, well, then we can just take theta to be a unitary matrix if we want. But here's the new thing, and this is the surprising thing. If gamma is not already unistochastic, well, there's this trick you could do. You could take theta, slice it up into its columns, stick each column into an otherwise empty n by n matrix. There'll be n of these matrices. They're called K1 through Kn. You can show these matrices satisfy an important identity called the Krauss identity. They are called so-called Krauss matrices, and they give what's called a Krauss decomposition of the dynamics. And then there's this beautiful theorem, Steinspring's theorem from the 1950s. The proof, the detailed proof is in the papers. I'm not going to have time to go through the proof here, but you can read the papers if you want to see it. If you enlarge your configuration space, then you can make everything unistochastic again. So even if your original system was not unistochastic, even if gamma isn't unistochastic, there isn't a unitary, this theorem means that you can always regard your system as part of some bigger system that is unistochastic and has a unitary evolution. And that's new and exciting, and it means that basically you can just focus your attention on the unitary case. You don't have to worry about these other cases. And this is where you start to think about applications to the theory of stochastic processes. I made no assumption this was a Markov process. This is a very general non-Markovian process. And we're saying that all of them can very naturally be simulated or encoded in a unitary process on Hilbert space. Hilbert space is the setting for quantum mechanics, for this emergent quantum mechanics. Hilbert space is the set of all the vectors. Question?
Could you hear me in Zoom land?
Yes, hello.
Hi, how you
Disembodied
doing?
voice, hello.
Good. Does this work also if the configuration space goes to infinity?
That's a fabulous question, right? I do not know. The Steinspring dilation theorem is generally applied to finite dimensional quantum systems. It would be a very interesting question to study under what circumstances this works in the infinite dimensional case. However, as you may know, how many of you heard the news of the Busy Beaver number? Did you hear about the fifth Busy Beaver number? Yeah, okay. So Busy Beaver number, very roughly speaking, is you have a very simple model of a computer called a Turing machine that has some number n of internal states that can change. You can write a script for it. And the question is, what is the longest an n-state Turing machine can run, such that if it ran one step more, it would provably have to go forever. What's the longest finite number of steps a Turing machine can go and halt and stop and be done, such that if any Turing machine of that size went one more step, it'd have to go forever. And it turns out that the first busy beaver number for a Turing machine of just one configuration is pretty simply just one, because you can't really write much programming for it. I think for two, it's like 6 or something like that. But the numbers grow staggeringly fast. And it was only just like a few days ago that people figured out the fifth busy beaver number. It's 42 million something. Right? The next busy beaver number, number 6, no one knows what it is. And we will never know what it is. Because the lower bound on it, lower bound, smallest it could be, is 10 to the 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 10. Okay. Now, this is simply a number that you cannot, like, this isn't a Google plex looks at this number and goes, oh my God, that's a huge number. Okay. Right. Finite numbers can be really, really big. And ultimately, I don't know if empirically there is truly any deep difference between something that is that big, a finite number of that size, a number so big that the axioms of set theory do not permit you to figure out how big it is, and something that is truly infinite. But I don't know. Anyway, the infinite dimensional case is something that is certainly worth further study. All right. I want to say a couple of things about the complex numbers. Notice in the original indivisible stochastic process, it's just a set of configurations and probabilities. There's no complex numbers anywhere. Quantum mechanics, there's complex numbers everywhere. Why? Well, for n bigger than 2, remember I said the 2 by 2 case was special. But for n bigger than 2, if you've got more than 2 configurations, your stochastic matrices are bigger than 2 by 2, 3 by 3, 4 by 4, higher. Then being unistochastic does not necessarily mean that you can take the unitary matrix to be real. In fact, what you'll generally find is the unitary that you need to get the unitary description has to involve the complex numbers or an algebraic construct that is isomorphic to the complex numbers. Hence, if you want to exploit this theorem, this connection between stochastic and quantum systems, and be able to use unitary evolution, you're going to need the complex numbers or something algebraically equivalent. But from this point of view, the Hilbert space picture is just a mathematical fiction anyway. So let's just help ourselves with complex numbers. You can do all these cool things with complex numbers. There's a comprehensive list of things. Actually, this is sort of a funny thing, right? This is a side note. Those of you who've done some quantum mechanics, you know that time reversal transformations involve not just a unitary transformation, but also like a complex conjugation transformation, which is a little weird because you think of I as a scalar that commutes with everything. It doesn't commute with everything. And in fact, what this is telling us is that the complex numbers aren't even really the true Clifford algebra that you want for quantum mechanics. You actually want a Clifford algebra called the pseudo-quaternions, which includes I, our familiar square root of minus 1, k, which is involution. If the complex conjugation operator squares to 1, because you do it twice, it does nothing, but it anti-commutes with it, because when it passes through I, it converts I to minus I, and then ik, which is a third element, and those 3 elements generate what's called the pseudo-quaternions. This was first noticed by Ernst Stuckelberg in 1960. Really underappreciated major player in the development of quantum mechanics and quantum field theory. That said, even though we do ultimately need this Clifford algebra, K does not show up in the definitions of observables. It's a very weird role that it plays in the theory. All right. Well, if the density matrix is a so-called rank 1 matrix means various ways to explain that in terms of like spectrum of eigenvalues, but for our purposes, it just means it's factorizable into a column vector and the adjoint, the complex conjugate transpose of that column vector outer producted together. If the density matrix is rank 1, it can be peeled apart into an n by 1 vector and its adjoint as an outer product. And then the von Neumann equation becomes the famous Schrodinger equation. I'm just saying this because I said before that the Schrodinger equation was a special case. The von Neumann equation it makes that explicit. But from this point of view, what we see is that wave functions in the Schrodinger equation are secondary pieces of derived mathematics. They're not primary ontological furniture. Like they're not part of the actual structure of the world. They're just interesting pieces of mathematical representation. The state vector or wave function there is also highly non-unique because this decomposition is insensitive to multiplying by an overall complex phase factor. We see from this, this construction that wave functions are not purely epistemic things. They include a blend of some epistemic ingredients, the initial probabilities that are encoded into rho, the density matrix, But also nomological information, because if you carefully look at them, you'll see that they're built not just out of those epistemic probabilities, but also out of the theta or unitary U matrix, which is ultimately encoding the dynamical laws in gamma in our model. Right, so the standard unitary Hilbert space formalism formally yields a divisible first-order differential equation for dynamics, the Schrödinger equation. All right, we can also go the other direction. This is now the quantum to stochastic direction. Given any unitarily evolving quantum system with an n-dimensional Hilbert space, pick a convenient orthonormal basis, write the unitary time evolution matrix in that basis, square its entries, and that, as we've seen multiple times, defines an indivisible stochastic process. Now you look at this and you go, wait a second, aren't I throwing out all kinds of valuable information? I mean, I square this, I lose all these complex numbers, I lose all this information in U. Certainly this can't give me an empirically adequate description. Empirically adequate means a description that is capable of correctly predicting experimental results in agreement with quantum mechanics. Au contraire, remember, all empirical results come from measurement processes. Certainly anyone defending textbook quantum mechanics is not going to dispute that. Okay? But in this picture, we don't have the idea that we have some abstract external agent or observer. Observers, measuring devices, they all have to be included as physical systems in the process. And when you do that, you put them into your indivisible stochastic process, just like every other system that you're modeling. And you pick your orthonormal basis. Well, you pick it to be a basis that labels distinguishable pointer values of the measuring device. Basis vectors that label distinct readings on the measuring device. Well, when you run the process, it's just inevitably going to happen because this stochastic matrix is giving you those probabilities that you're going to get exactly the correct probabilistic predictions for the readings on that measuring device. It will just deliver the correct answers. And that means by construction, this is an empirically adequate description. But it does require that you stick the measuring device in as another system. So how are we to interpret the phases information, stuff we're losing by mod squaring? The way to interpret them is, if you don't want to put the measuring device into your system, if you prefer a simpler model where you don't actually model the measuring device, then you want to hold on to that phase information, right? Because that phase information is a proxy for the missing measuring device, right? So it's just a mathematical shorthand. If you don't want to actually model the measuring device, then sure, use U, keep the phases. But if you're like, want to ask what's actually going on is you put the measuring device in, and then you don't need the phases anymore. Okay. Now we have a framework to explain the theoretical grounds why the well-known Markov or divisibility approximations often work so well in applications. This is I retrocausally prepared this part of the talk in response to the question that I got. Okay. All right, so consider a composite system, a subject system, and an environment. Again, we're just putting the systems together in one big stochastic system. And suppose that for each configuration I of the subject system, the first system, the system being measured, the environment has a corresponding configuration that depends on the configuration of the system. Think of this as, this is the configuration E of I, means the environment sees or has recorded that the configuration of the system is I. Suppose that the interactions between them, as encoded in this stochastic matrix, delivers the following joint probabilities at a time t prime. This is not fancy, this is classical correlation. This just says that whatever probabilities you assign to the configurations of the subject system, the environment has definitely read in that configuration, that's Kronecker delta, with unit probability environment is in the configuration that agrees with the reading of the system. Right, that's what it says. Then from classical marginalization, just marginalize over the environment, ask what's going on with the subject system alone, what you will find, or something over the configurations of the environment, that we get the following result on the right-hand side. With a stochastic matrix connecting t prime to t, and you can show that that stochastic matrix connects the evolutions, just like you would have expected. That is, due to the correlating interaction with the environment, there is automatically a new division event at t prime playing the role of what we were calling t equals 0 before. We expect that for systems interacting robustly and repeatedly at a high rate with an eavesdropping environment, that we're going to get these kinds of division events all the time. And this explains why the evolution breaks up into steps. And this is where the Markov or divisibility assumption comes from. It's easy to show that at that special time t prime where the environment read things in, the density matrix rho, which had all these diagonal entries, momentarily becomes diagonal again. The coherences vanish. We call that decoherence. So we learn, again, what the off-diagonal entries are doing. They're coherences. They're an artifact of the indivisible dynamics. And decoherence, as seen from the Hilbert space unitary perspective, is really just the prosaic leakage of correlations in the environment when seen in the original underlying stochastic process. Now you might be going, what about entanglement? In 1935, Schrödinger wrote a paper in which he said on the first page, entanglement is not a, but the characteristic feature that makes quantum systems different from classical systems. Well, let's look at that. Suppose we've got two subsystems, A and B, that belong to a composite system. And let's suppose that initially they are separate, uncorrelated, not interacting, just like we would set up an entanglement experiment. Right? So before sometime t prime at which maybe they'll interact, before that, the overall stochastic matrix of the two systems divides. Here I'm using an abbreviated notation instead of saying from 0 to t, I'm just saying t, but these are from 0 to t. Okay? So for all times before any possible interaction, we get what's called a tensor product, which just means you get two separate stochastic matrices that describe the two systems individually. They each have their own individual stochastic matrix. However, transition matrices like these, they go from 0 all the way to whatever, they're giant leaps. They encode cumulative statistical information. And that means that if there is an interaction at t prime, and at that interaction there's a correlation, and now the stochastic matrix suddenly does not factorize like this, it will continue to fail to factorize for all later times. Right? So if an interaction happens at any t prime, then for all t bigger than t prime, we will fail to have this factorization. There won't be an individual dynamics for each system, only a composite dynamics that doesn't split apart. That's exactly entanglement. It already looks like entanglement. But notice phrased entirely in stochastic language, no mention of Hilbert spaces. But now suppose that an environment or a device or whatever comes in and reads the configuration of the first system A. That produces a division event that we just saw. The division event means that now at some t double prime, when the environment came in and read the configuration system, the evolution will now divide, it will split. And if by the time t double prime has happened, the systems are far apart and not capable of interacting, and we focus on the purple matrix that describes all the subsequent time evolution that we now have available to us because of the division event, well, that purple matrix will go back to tensor factorizing. And this is, of course, what we call the breakdown and entanglement under measurement. Again, all phrased classically. Okay. Now, there's some language that John Bell introduced to distinguish between merely the things we observe about a system, so-called observables, and maybe properties the system intrinsically has. He called those not observables, but beables, to be, or not to be, definitely to be, beables. Just random variables on a configuration space from this perspective, right? So a beable is just a random variable that just means that it's some numerical magnitude assigned to whichever configuration 1 through n the system is in, and maybe also depends on the time. So it's a list of possible magnitudes. I can arrange them into a diagonal matrix, A1 through AN. Those are the values that this variable could have depending on the configuration 1 through n the system is in and on the time. And you can just check, this is a simple calculation, that statistical averages of this thing can be computed by multiplying that matrix by the system density matrix at the time t and tracing, doing a matrix trace, which is the standard formula for how we compute averages in quantum mechanics. If A happens to be a projector, meaning that it assigns 1 to a single configuration and 0 to all the others, it's basically a true or false statement with 1 is true, 0 is false. Pi is the question, is the configuration of the system in fact I? Call that an elementary projector. If we also assume the density matrix is rank 1, which is the usual simplification, then that expectation value formula becomes the Born rule. The probability the system is in its ith configuration is the mod squared of the wave function's ith component. I said before that modeling the measurement process is an overall unistochastic process leads to the same predictions you get from the overall quantum system. But you might ask, well, on the one hand, I've got these beables, but what if my measuring device is trying to measure something that's not one of these diagonal matrices? Right? I'll say in a moment exactly how that works, but let me just say right now, well, by construction, you're going to get the correct results. We already show that the measurement process modeled in this way will yield the correct results. So what's going on? The measuring device is not in the case where it's measuring a non-diagonal matrix. It's not measuring a true beable, a true actual value assigned to the system. It's picking up an emergent pattern in the system that, as far as the measuring device is concerned, looks just like a beable, but is not. And so the claim is, instead of all the observables of a quantum system include the actual beables, you're revealing actual values the system has, and these emergent patterns that, as far as any external measuring device is concerned, look and behave just like beables do, and they make up all the observables. And together with the beables, The emergibles combine to give you a non-commutative algebra, matrices that don't commute, the full non-commutative algebra for the quantum system. Okay. So this is a couple of slides on how the measurement process works. If you want to measure some emergible, some emergence, observable, emergible, in general, in quantum mechanics, we take it to be a self-adjoint operator. That means it's got a spectral decomposition. As usual stuff, we model it. This is all identical to the environment case, right? We introduce a measuring device as another system in the system. I'm just going through the details of what I said in words, right? No gerrymandering or fine tuning. We just evolve this stochastic process like we did in the environment decoherence case. Here's an explicit example of a unitary that you could use to underlie the unistochastic matrix we're talking about here. This is just one example. Anyway, the point is the results come out exactly right. At the end of the measuring process, the probability that the measuring device D is in its configuration little d of alpha prime, meaning this is the configuration in which its internal configuration little d records the value alpha prime of the emergible being measured, is in fact the absolute value squared of the wave function of the subject system expressed in the basis of that emergence. So it's exactly what you expect. And this is just a textbook Born rule for the probability of the appropriate measurement outcome. And then you can also show that if you condition on the measuring results, you can safely write down a conditional probability. What is the conditional probability the subject system S is in its configuration I at a later time t prime? Given the measurement result, you can show that that is given by wave function collapse. Wave function collapse from this perspective just turns out to be conditioning on the measurement result, which is all valid and allowable because the measurement itself was a division event. You can condition on it. Everything works out just perfectly. Just perfectly. Okay. So we arrive at the stochastic quantum correspondence, according to which the Hilbert space formalism serves as a form of analytical mechanics, if you want, for stochastic systems. Just like in classical physics, you take Newtonian formulation, you can reformulate it as Lagrangians, or in the Hamiltonian phase space formulation, which is a nice first order formulation. We're saying that the Hilbert space formalism is like that, but not for a deterministic Newtonian system. It is the Hamiltonian mechanics for an indivisible stochastic system. And this correspondence, to be clear, is many to one in both directions, but that's also true for Hamiltonian mechanics for a classical system. A given Newtonian system will have infinitely many different Hamiltonian descriptions, and a given Hamiltonian description can describe many, many possible classical systems. After all, we had to pick an orthonormal basis to go from a quantum system to the stochastic system. That's like picking a canonical frame in a Hamiltonian system, because you do canonical transformations which are homologous to basis transformations. Okay. And like any form of analytical mechanics, Hilbert space formalism is super powerful, great mathematical tools. We've used it to design dynamics in a very systematic way. If you want to create a new model that didn't exist before, you don't want to use Newtonian mechanics. You want to use something like Hamiltonian or Lagrangian mechanics. These are much better for choosing or systematically selecting dynamical ones. Okay, this is the final part of the talk. Locality. You might be thinking to yourself, okay, that all sounds great, but it sounds like a hidden variables theory. We know those are bad. But are they? Okay, well, first a little bit of conventional wisdom. So depending on who you ask, you may hear the following about locality or positive locality. You might hear that, oh, there are no-go theorems. Haven't you heard of Bell's theorem? No-go theorems that rule out hidden variables. Hidden variables are ruled out. In fact, if you go look at the 2022 Physics Nobel Prize for Aspect, Clauser, and Zeiland, and you look at the press release, it says they proved hidden variables don't exist. That's what it says. That's totally false. Totally false. Okay. Another thing you might hear is that hidden variables theories are possible, not ruled out, but if you introduce them, then you're introducing non-locality or non-local causation, depends on whom you ask. We don't like those. So don't do that and just use textbook quantum theory and then there's no non-locality. Right? That's what you might hear. Or you might hear quantum theory is just unavoidably non-local or non-locally causal, with or without hidden variables. Which of these is what Bell actually said? We hear about Bell's theorem, and people say lots of things about it. One of these three things is what Bell said. Anyone?
Second, I think.
The second?
I don't know.
Third.
Okay, so if you ask a crowd of students, grad students, even professors, they'll often say two. Wrong. 3 was what Bell said. Bell said quantum mechanics was just non-local. That's what Bell was trying to prove. Right? They're all mutually inconsistent, of course, these statements. Bell, according to Bell himself, his theorem was actually saying 3. Now, if that's your point of view, then there's actually no danger with hidden variables because Bell's like, the non-locality is out of the barn. You can't save locality. So you might as well have a picture of which stuff is really happening. If you think that the choice is between hidden variables and locality or non-locality, then you might think that you have some choice over the matter. Bell said you did not. In fact, that was Bell's point. He liked a particular hidden variables theory called Bohm mechanics. And he was trying to show that the non-locality wasn't just about Bohm mechanics. It was a general problem. So you might as well go with the hidden variables. But I'm actually going to challenge this assertion from Bell. So let me just say a little bit about non-locality.
Before you move on, maybe you're about to explain, but what's the difference between causally non-local and non-local?
Wonderful question. That's going to be on the next 2 slides. Lovely question. There's a lot of retro causality going on here. It's great. Good. Okay. So let me just say a little bit about non-locality. When someone says, oh, that's non-local, what do they mean? Well, in Newtonian mechanics, there's a perfectly clear way to identify what non-locality means. In Newtonian mechanics, if you've got an action at a distance force, like Newton's law of gravity, right? There's a force and it's non-zero, and it instantly changes the 2 systems, right? It acts on both systems simultaneously, instantly, regardless of the distance. That is obviously manifestly non-local. That's what we mean by non-local, okay? The trouble is that when you leave Newtonian mechanics and E&M and the familiar bounds of Newtonian-ish physics, we don't have forces and potentials anymore. There are no forces in the fundamental level of quantum mechanics, for example. So it's just not clear what non-locality means. What do we mean by non-locality? There isn't a force anymore. So like, when someone asks, is quantum theory non-local? What do you mean non-local? What do you even mean? The usual thing that people do here is they say, well, I don't know about force non-locality, but let's ask about causal non-locality. Are there cause and effect relationships that are non-local? Because not forces anymore, so let's go to causation. And the problem with this is, as any philosopher, certainly any analytic philosopher will tell you, causation is a minefield from which no one will ever return. Okay? Once you start saying, maybe we should just check causal locality, you're in a world of pain. Which hopefully I'll say something about helping. But this is a dangerous move. Now, let's just get a sense of why this is going to be hard. So quantum theory involves probabilistic rather than deterministic relationships between observations. So there's just not going to be a tight linkage between cause and effect pairings anymore. You do something here, maybe it'll change something there, maybe it won't. It's probabilistic now. So it's not like a nice, tight relationship like it was. Moreover, there are theorems that say that you cannot use quantum mechanics to send controllable messages instantaneously. This is called the no communication or signaling theorem. So you can't rely on that. You can't ask, well, can you send messages? Well, no. So that's not going to be a way to check non-locality. So it's not immediately obvious whether there is non-locality or non-local causation in quantum theory yet. Okay. Here's one way to think about this problem, right? So there's a case to be made. This philosopher John Norton at Pittsburgh who wrote this wonderful paper called Causation is Folk Science. I highly recommend it to everybody. It's beautifully written. It's free on his website. That causal talk is just folk science. I mean, if you specify the state of the whole universe and evolve the state forward or back with the differential equations in Newtonian mechanics or whatever, right? You get the whole description of nature without anyone talking about this rock causing that rock to move. Is causal talk just like an idle wheel that we can add on? Humans can't see the whole state of the universe, so we just use causal language, cause and effect, to summarize or to simplify because we just can't see everything. Is causation really in the microphysics itself? Norton would say no. I think a lot of people might question whether there's actually causation there. But of course, if causation is not a part of the fundamental laws of physics, then it doesn't make any sense to ask whether quantum theory, a fundamental physical theory, is causally anything. If there's no causation at the fundamental level, then what are we even doing? The question doesn't even make any sense. Let's address those who take causal locality seriously. Because if you don't believe there's causation, then there's no non-locality in quantum mechanics is already good. But let's take seriously those who think that there is a meaningful notion of causation, and we can meaningfully talk about cause and effect relationships being local and non-local. Let's show how to make quantum theory hospitable to causal talk of causal influences. We're going to start with a very simple attempt at a definition of causal locality. Causal influences cannot propagate faster than light. That's going to be our working example. Notice this is a condition on any causal influences that happen to be there. Nature's got causal influences on it, according to this view, and any that happen to be there must obey this. This is not a statement that in some situations there have to exist causal relationships. We're not saying, oh, that's a situation in which there must be a causal relationship. We're just saying that if there happen to be any causal relationships lying around, they have to obey this rule. In their famous 1935 paper, which, how many of you have read the original EPR Einstein-Podolsky-Rosen paper? Oh, such a shame. It's a beautiful paper, and not very long. Not by today's standards, anyway. Beautifully written. Although Einstein was angry because Podolsky wrote it, and Einstein didn't think he did a good job, whatever. Anyway, so Einstein-Podolsky-Rosen wrote this paper. They used an early version of what Schrodinger later that year called quantum steering, which is a term of art that people use now. The idea is very simple. If you have two particles, they're prepared in an entangled wave function, and then separated in space. A measurement of one particle in a chosen orthonormal basis will collapse the other particle to the same orthonormal basis. And by choosing which basis you measure the first particle in, it's like you are choosing which basis the other particle collapses in. It's like you're steering the other particle from far away. You cannot control exactly which vector the second system gets into. You know, it could end up in several vectors, but you can control that it will be a vector in one basis or another. So you can't send a message this way. You can't control exactly what answer is obtained, but you can, like, seemingly cause the system to collapse in whatever basis you want far away. But the no communication theorem, like I said before, prohibits you from using this to send controllable messages remarkably. So you can't pick which specific state vector wave function you get, just which basis it's in. Now, what did Einstein-Podolsky-Rosen say about this? Well, in their paper, they said, there's no way you're actually changing something instantly far away. That would be non-local. We don't believe in that. So the only alternative is that the second particle must already have known what result it was going to be in before you did your experiment. If you're not changing it in any way, but somehow you're like picking what basis it's going to be in, it must have already had that information before you did the experiment. Basically, they're saying the only way to get away from non-locality is to have hidden variables. This is completely the opposite of the story that you usually hear. This isn't hidden variables imply non-locality. It's that hidden variables are the only way to save locality. That's what EPR was saying. Okay? And it concluded this meant quantum theory was incomplete. There have to be hidden variables. Okay? Now, there are contestable implications here for non-local causation, right? So, you know, you could think of this as spooky action at a distance. Anyway, this whole reading is contestable because it relies on wave function collapse, which a lot of people don't think is a fundamental process. Certainly, it's not a part of the version of quantum theory that I was talking about earlier. But crucially, it also depends on a particular theory of causation, interventionist causation. Interventionist causation is the idea that to say that A causally influences B is to say that if an abstract observer or agent intervenes on A, they can produce some effect at B. But this is as bad as the measurement problem. It relies on this abstract agent coming in and manipulating one of the variables. That's fine if you want to do a medical study. But if you're talking about fundamental laws of physics, you don't want to have an abstract agent. Agents are supposed to be made of atoms, right? What's going on at the level of the atoms? Interventionist theory of causation is clearly not fundamental. Okay? So this argument, EPR argument, depended on that. One observer manipulating, intervening on their particle and changing another one. That's the interventionist conception of causation. That's another serious problem. What did Bell do in his no-go theorem in 1964? The famous Bell theorem that you see in the back of Griffith's, you know, Griffith's epilogue when he does the Bell theorem. He's doing the 1964 version of Bell's theorem. So Bell was inspired by the EP argument. He was inspired also by an existing hidden variables theory, the Bohm-Beam mechanics or de Broglie pilot wave theory, to write a paper called On the Einstein-Podolsky-Rosen Paradox. He was very clear what this paper was about. He was attempting to tackle the question of non-local causation head-on. He viewed the EP argument as creating a logical fork. Either non-locality and no hidden variables, because the hidden variables, the thing you did here, causes somehow the thing far away to change, or that there's a predetermined value for that thing and that you don't need non-locality, at least according to EPR. He said either you have hidden variables and locality or no hidden variables and non-locality. What he wanted to show was that, in fact, this was a false fork, that even with hidden variables, you still have non-locality. This is the only part of the theorem many people remember. Bell showing that hidden variables lead to non-locality. But that wasn't the whole argument. The argument was that without hidden variables, there's still non-locality. So he just was showing that there's just non-locality whether you like it or not. Okay? He considered measurement deterministic hidden variables theories like Bowlby mechanics, in which the hidden variables dictated specific measurement outcomes. And his goal was to show the second prong of the four could not ultimately save possible locality. Okay? So there's this setup. This is in the books, right? There's hidden variables. There's measurement results A and B. Little a, little b represent local measurement settings. He has these assumptions. The measurement result A only depends on the settings for A, the settings that one observer, the one local to A, is using, and maybe hidden variables lambda. Similarly for B. There's also an implicit assumption of an interventionist conception of causation because you've got agents doing these experiments. Crucially, right, he assumes that when you do this experiment over many, many, many entangled pairs, 10,000 times, you collect statistics on all the results, all the capital A results, all the capital B results, capital A for the first particle, capital B for the second particle. Well, and then you average them, you get this correlation function, this expectation value of the product of the A's and B's. And there's this crucial factorization he needs in the result that shows that. That's crucial to making Bell's theorem work. And it's ironic that Bell's results in this theorem hinge on assumptions about expectation values, because around the same time, Bell wrote a paper in which he challenged an older anti-hidden variables theorem of von Neumann from 1932, pointing out that von Neumann had also made an unjustified assumption about expectation values. Now Bell is making an assumption about expectation values that we're going to challenge in a moment. Actually, Greta Herrmann got there first in the 1930s, but her work was, for reasons that are complicated, were ignored, and then she went off to fight the Nazis. So she became a freedom fighter. It's like fucking awesome. Okay. All right. So with that factorization, with that statement about expectation values, you can derive the following inequality relating correlations between measurement settings for different choices of measurement settings. You get this inequality, the famous Bell inequality. Quantum theory predicts that this inequality will be violated, and then experiments were done and show that it was violated. And as we know, this means there are no hidden variables, right? Not what it means, but that's what the Nobel Prize was for. And so if you take this inequality to be the result of Bell's assumptions, Bell's causal locality assumptions, the assumptions that he baked into his theorem, his interventions, take all those things together, they imply this inequality is violated, and therefore, even with hidden variables, quantum theory is non-local, involves non-local causation, and that's a form of non-locality. Okay, now there are some loopholes, some well-known, some less well-known. Provided one doesn't take the EPR argument to be definitive, again, because it also depended on interventionist causation, a wave function collapse, Bell's 1964 argument leaves open several possibilities. Could maybe nature described by a non-locally causal measurement in terms of hidden variables theory? It's worth noting that Bowlby mechanics explicitly has a force or a potential that's not local. Or you could have a measurement stochastic hidden variable theory, where the measurement results are not uniquely dictated by the hidden variables, or a formulation of quantum theory that attempts to just eschew hidden variables completely. Okay? But Bell's 1964 argument certainly does not rule out hidden variables altogether. Then a crucial follow-up, 1975. Bell attempted to generalize his 1964 theorem to encompass the second and third possibilities and stamp out the possibility of locality for good. Textbook quantum theory for all possible hidden variables theories. And remarkably, although he doesn't say this 1975 proof does not rely on interventionism. All the other no-go results about non-locality rely on intervention causation, but this 1975 paper almost uniquely does not. And so this is a possible way out. Not relying on interventionist causation, maybe Bell is tapping into a more fundamental notion of causation and then showing that quantum mechanics is non-local under that notion of causation. Okay. So his argument was much more general, applied to all possible stochastic measurement type theories, with or without hidden variables. That includes the textbook theory. He wanted to show that all empirically adequate theories involve non-local causation. One problem is when the measurement outcomes are stochastic, there's no tight linkages anymore. What do you mean by causation? And if you give up interventionism, what do you mean by causation? What does he mean by causation now? Another problem. There's a crucial factorization he needed in the expectation value, and it's simply not available now. The theorem can't work. So there's some central problems here. How does Bell deal with them? Well, he introduces a concept of local beables, matters of fact that are truly there out in spacetime, associated with points in spacetime. He explains this in a later lecture in 1990. He says the beables of the theory of those entities in which are at least tentatively taken seriously as corresponding to the real. Local beables are those which are definitely associated with particular space-time regions. In particular, by replacing abstract measurement outcomes by agents with local beables, maybe you don't have to rely on interventionism anymore. Okay, which is good. But even then, Bell pointed to another big problem. We're frustrated with the vagueness of contemporary quantum mechanics. We'll hunt in vain in the textbooks for what the local beables are. Blah, 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 blah. We'll do the best we can with these other ill-defined local beables, while hoping always for a more serious reformulation of quantum mechanics, where the local beables are explicit and mathematical rather than implicit and vague. And one of the goals of the talk was to lay out just a reformulation. So what does Bell try to do? In his 1975 theorem, and then in a 1990 lecture, they're describing what he was trying to do. He starts with a principle that's basically our principle. Causal locality means the direct causes and effects of events are nearby, and even the indirect causes and effects are no further away than the velocity of light. That's what we said. But Bell says the above principle of local causality is not yet sufficiently sharp and clean for mathematics. This is Bell saying that it's too vague. Just before he states his second attempted principle, he includes the following warning that apparently not enough people take it seriously. Now, it is precisely in cleaning up intuitive ideas from mathematics that one is likely to throw out the baby with the bathwater. So the next step should be viewed with the utmost suspicion. In red, okay? So what does he do? Similar setup, but now lambda is not hidden variables, it's beables in some general sense. And we have far separate measurement outcomes, local measurement settings. We can now regard measurement outcomes and measurement settings as local matters of fact, not necessarily carried out by agents. That's good. But now Bell has this problem. What does he mean by causality? This is what Bell takes causality to imply. He doesn't define causal relationships because, as any metaphysician will tell you, that's really hard. But he says in any reasonable theory in which there is local causal influences in the microphysics, this should be a downstream consequence. A downstream consequence that if it's violated means that you just can't possibly have a good microphysical theory of local causation. He takes the downstream consequence of a good microphysical theory of local causation to be the statement that there is a sufficiently rich collection of local beables lambda in the overlap of the past light cones of A and B, such that the conditional probability of A having a particular outcome value conditioned on all the other data, measurement setting for A, measurement setting for B far away, the result B itself, the beables lambda simplifies. And the dependence on the measurement result B and the settings B go away. They're screened off. There's a rich enough set of beables in the overlap of the past light cones of A and B, such that when you condition on them, that you're allowed to condition them, and once you do, they screen off all the dependence on everything that was happening with B. That's what he takes to be inevitable downstream consequence of the good theory of causation. Similarly for the B system. Now, in general, this is just a general statement of probability theory. This requires no assumptions. But if you apply the previous statements to the statement below, you get this factorization. Again, a factorization. Bell needs a factorization. This is the factorization he needed to generalize his earlier 1964 theorem. He then takes that factorization and plugs it back into the expectation value formula, does a very similar calculation, and he gets back the Bell inequality, or a generalization called the Clauser-Horn-Shimoni-Holt inequality that was actually first derived 6 years later, in 1969. So any measurement stochastic theory, any textbook quantum theory, anything, any theory at all that satisfies his local causality assumptions will imply the Bell inequality or the CHSH inequality. We know that that is violated empirically, and that means that quantum theory is simply non-locally causal according to Bell. But Bell's new principle of local causality is not as simple and straightforward as you might think. It tucks in a new implicit assumption. I don't know how Bell found out about this principle. He doesn't use the word Reichenbach anywhere in any of his writings, as far as I know. Maybe he heard of it and didn't know who came up with it. Maybe he independently came up with it. But he's using a principle called Reichenbach's principle of common causes. In modern form, Reichenbach's principle says that if A and B are variables that are correlated, so the joint probability does not factorize, they're not independent, but A and B do not causally influence each other, then we positively assert there must exist some other variable C, such that when we condition on C, screens off the correlation and we get factorization. Notice this is identical to what Bell wrote down. This is a more general version of what Bell wrote down. This is called Reichenbach's principle of common causation. Notice that we're not just saying that any causal influences that happen to be around must satisfy some property. We're asserting that in some situations there must exist causal influences. They must positively exist in certain circumstances. Okay. So this was Bell's principle, and this is clearly an application of Reichenbach's principle, common causes. Bell is asserting that if A and B are beables that are correlated but space-like separated, then there must exist causal influences. There must exist beables, a rich enough set of local beables in the overlap of their past light cone that, and you can condition on the values of those beables, and once you do, it screens off the correlation. Bell takes that to be a downstream consequence of a good microphysical theory of local causation. The common cause is played by those local beables in the overlap of past light cones. Essentially, lacking a concrete microphysical theory of causal influences, Bell assumed that any good such theory should entail local Reichenbachian common cause variables. Now, there's a term a lot, I keep saying causal locality versus local causality. This is just a side note. Wayne Mervold has made a big deal about this. He's a philosopher of physics. But I'll mention it. Causal locality is this more basic condition, basically Bell's first condition, that any causal influences that happen to be around must not go faster than light, whereas local causality is what Bell was saying. There must, in some cases, be causal influences that must exist in certain circumstances. It's a positive assertion that sometimes there must be causal influences in certain circumstances. It's a stronger assertion. Now, there's some good reasons to doubt Reichenbach. First of all, there are all kinds of counterexamples to Reichenbach that philosophers have come up with. That's already a sign that this is a dangerous principle to rest your theory on. But it's also far from obvious to require it as part of a condition on causal locality. I mean, one thing it assumes that every common cause is a variable. Not all common causes are variables. Okay. Bill Unruh of the famous Unruh effect wrote in 2002, the correlations do not arise mysteriously somehow in the development of a widely spaced system. They don't require some mysterious non-local action to be explained. They're simply there due to the evolution from a common cause in interaction. What Bill Unruh is pointing out is that to get two things entangled, there does have to be a common cause of the entanglement in interaction. But interactions are not variables. They're not beables. Bell was assuming that common causes had to be beables, central to how he did his theorem. But interaction is not a beable. An interaction isn't some value, some number that has some specific answer in a given state of the system. It's much more abstract and not the kind of thing that plays the correct role. So Bell was using too narrow a conception of what a common cause had to be. He had to do that because otherwise he couldn't get his theorem to work. But that's not a good excuse. Interactions are just not Reichenbachian variables. Now, there's a whole bunch of other theorems. I mentioned the GHD theorem, EPR, a bunch of independent interventionist conceptions of causation. There's a whole bunch of new theorems, the so-called Wigner's friend experiment type theorems they call them the local friendliness theorems and stuff. But if you read all these papers, you gotta read the appendices though. So let's put these appendices. You'll see that they at various places insert the existence of laws that we don't have any good reason to think are there, and certainly wouldn't be there for an indivisible system. So they're all cheats, at least so far. But it's not clear how one would derive the Bell inequality or prove any of these theorems when working at the level of the atoms without interventionist causation, without any of those assumptions and negative measuring devices. I should say, by the way, that Everetti and many worlders already did not the premises of the theorems capture the correct notion of locality, but whatever. I'm going to show that the new unistochastic formulation we've been talking about, this indivisible quantum stochastic correspondence, exploits these loopholes to allow for both an improved criterion for causal locality and show that quantum theory is causally local according to that criterion. And the key idea comes from causal modeling. There's a theory of causal modeling, in which one considers a set of random variables related by a collection of basic directed conditional probabilities. So what this represents is just an abstract diagram. You've got a bunch of variables that can vary in value depending on the run of the system. They're contingent. They can vary from one run to another. And what this diagram is saying is that A is causally influenced by the variables B, C, and D. But this causal influence has a very concrete law-like meaning. Okay? What it means is that our model supplies us with a law that says that there is a specific conditional probability distribution for the value of A, given the specific values for B, C, and D. That is, among our laws is this statement, this conditional probability. It's in our laws. That's a very concrete meaning to the idea of a causal influence. We call B, C, and D the exogenous variables. They can fluctuate from run to run, and then A is the endogenous variable. Its value is probabilistically influenced by B, C, and D. Okay, well, in a concrete instantiation of this Bayesian network, one is going to have some contingent, depends on the run, joint probability distribution for B, C, and D. I'm using green there to indicate it is a contingent probability. This will then induce a contingent standalone probability distribution for A, according to this multilinear relationship. But you see, there's a brown P in there. That brown P is a law-like P. That's not contingent. That law-like P is built in, it's hard-coded into the model. It's part of the laws. And notice it translates the probability distribution for B, C, and D into a contingent probability distribution for A. It's doing the job of a causal mediator. Now, you might go, well, wait a second. I can simply define other conditional probabilities. Well, why can't I use Bayes' theorem or define the other ones? Well, let's do that. Let's define a different conditional probability. Here is a conditional probability of B given the values A, C, and D. But you'll notice that to define it, according to Bayes' theorem, we have to, this is just now unrolling the definitions of joint and conditional probabilities and marginally all the usual Bayes' theorem stuff. What you see is that this is given by a very complicated mixture of contingent information, the green P's, and a nonlinear combination of the brown P's, the law-like P's. This is clearly not a hard-coded fact into the model. It's not of the same status as the brown P. The basic directed conditional probabilities, directed from BCD to A, supplied by the Bayesian network have a more fundamental status. They're parts of the fixed laws of the model. So they have more of a credible status to be like, to be law-like and have a causal reading. Okay. Crucially, Bayesian networks have been a non-interventionist causal reading. If the model supplies a basic directed conditional probability distribution for A, conditioned on B, C, and D, then any stochastic fluctuations in B, C, and D that are contingent every time we run the model will dictate the stochastic fluctuations in A. Taking this seriously, one can argue that by supplying these conditional probabilities in laws, the model is asserting that B, C, and D exerts a causal influence on A. And this would be my definition of causal influences. Notice how the directedness of these conditional probabilities nicely captures the asymmetric nature of cause and effect. There's an asymmetric relationship between causes and their effects. And this captures that because there's a direction to here, B, C, and D to A. You can't reverse it without doing those shenanigans that we said before, right, that make it not fundamental. But yet it does this without privileging an arrow of time. It threads a very fine needle. So here's one almost obvious problem with any claim theory of causation. If nature is fundamentally time reversal invariant, and causes happen before effects, how are those compatible? Either nature really is not time reversal invariant, which would go against all of our microphysical laws of nature that we know of so far, with the exception of some weak interaction stuff, but then you have to argue this CPT of formula. Go into that. Okay? But roughly speaking, the laws of nature are almost exactly time reversal invariant, certainly not in a way that would be, the violations of time reversal invariance aren't helpful in the way that they would give us asymmetric cause and effect in time. So it would seem like this is just a no-go. You can't have cause and effect relationships because if causes always come before their effects, well, that's incompatible with the fact that nature doesn't pick out a time direction. Notice that this asymmetry says nothing about time. I didn't say whether A was before or after B, C, and D. It's directedness and asymmetry between cause and effects, but without privileging a direction of time. And that's a very fine needle to thread. Okay, so this new formulation of quantum theory, it's based on microphysical laws that consist of directed conditional probabilities. That's what those gammas are. They're exactly directed conditional probabilities, just like the kinds of these Bayesian networks. So now we have a hospitable domain for causal talk. One can arguably apply a causal reading to those directed conditional probabilities and say that the laws are in fact causal laws. In that sense, you can regard quantum theory as a microphysical theory of causation par excellence. And now we have the microphysical notion of causation with which we can talk about whether the causation is local. Consider an overall unistochastic system consisting of two subsystems Q and R. The overall system's microphysical conditional probabilities take this form. This is just our gamma entries again. I'm now going to define what it means for Q to be free of causal influences of R over some time interval from 0 to t, if after marginalizing over R, the resulting conditional probability distribution has no dependence on the initial R naught. So in words, if I focus just on system Q, then I can just drop all the dependence on R. Because these have a causal reading, this is a statement that there's causal independence between systems over that time interval. Now I can state an improved principle of causal locality. A theory with microphysical directed conditional probabilities will be called causally local if any pair of localized systems Q and R that remain at spaceless separation in the given situation never exert causal influences on each other in the sense that those directed conditional probabilities for Q are independent of R and vice versa. This is a precise statement now, what I mean by causal locality, and it is now straightforward to show this principle is satisfied by quantum mechanics. Start with systems in space like separation. Standard rule is that the dynamic separates, factorizes like this. We write down the corresponding gammas. And now you can just check that these conditional probabilities factorize because this is nothing other than a restatement of that tensor factorization. And now if you marginalize over the second system, you get this independence just like we expected. QED, that's it. By contrast, suppose that Q and R are not kept at space separation. Suppose they do interact at some interaction time t prime. Well, at that interaction time, the time evolution operator will fail to factorize. This will entail a failure of factorization of gamma that will persist at all later times. That's exactly entanglement again, because gamma encodes cumulative statistical effects, and you'll no longer have this factorization, at least until the next division event. This breakdown of factorization gamma is, again, the entanglement manifest level of the underlying indivisible unit stochastic process. And so we say the two systems are, in fact, exerting causal influence on each other, stemming from their local interaction at T prime. That's the common cause. There is a common cause. It's an interaction, not a Reichenbachian variable. And now we can revisit the EPR argument. Go back to the original EPR argument. Alice has system A, Bob has system B. This is the space-time diagram. The two systems Q and R. I'm sorry, Alice is A, Bob is B, and the two systems they're studying that are entangled with Q and R. Q and R are local with each other up until that time T prime, that's that line there. They interact, and then they travel in separate directions. Although that looks diagonal, they're really going sideways. It's just that time is going up. Really, they're just sort of separating, but when you lay that over time, it looks like diagonal lines. Q reaches Alice, R reaches Bob, and now we've got the Q Alice system and the R Bob system. You can now show by a straightforward calculation that Bob does not exert causal influences on Alice, and Alice doesn't exert causal influences on Bob, even if they're doing measurements in the required sense. If you just compute the conditional probability distribution for Alice's configuration at time t, including everything it could possibly depend on, you will find in this calculation that all of Bob's stuff disappears. So Bob is not exerting a causal influence on Alice after all. Now, the two systems, Q and R, are exerting causal influences on Alice, but they're inter-pass light cones. That's totally fine. The only causal influences on A come from Q and R, which are both in the past light cones effect. So we're done. Conclusion. In short, consider a stochastic process over a fixed choice of orthogonal basis without imposing all the intricate nomological structure of a textbook non-Markovian stochastic process, and you get quantum. One then arrives at what appears to be a causally local hidden variables theory based on simpler axioms than textbook quantum theory. Those axioms were just the definition of an indivisible stochastic system I began with. Right? Not even mentioned if Hilbert spaces are complex numbers or self-adjoint, whatever. Arguably, with no measurement problem anymore, there's no subjective, oh, when is the measurement done? When do we convert the mathematical symbols to probabilities? We don't have to do that anymore. Just model the whole thing as a stochastic process. And deflating a lot of the exotic talk about quantum phenomena like entanglement interference. And there are many prospects for future directions, applications to dynamical systems and stochastic processes. That's I'm particularly interested in that. You've got some very annoying indivisible and non-Markovian process. Maybe simulating it as a quantum process using this formalism will make things easier to do. New algorithms for doing quantum simulations, new ways to deal with quantum causal models, implications for old problems in physical mechanics. Physical mechanics is filled with all these deep problems that get much easier if you just allow your laws to be directed conditional probabilities. Possible ramifications for algebra first approaches to quantum theory, like C-star algebraic and GNS construction type approaches, and open questions like this question of unitarily unequivalent GNS representations, generalizations of quantum theory. And you're starting with new axioms. New axioms means new knobs, new things you can turn, and maybe new generalizations that might have been very difficult to see if you're starting from the Hilbert space formulation. And finally, maybe new possibilities for quantum gravity. And that is it. Thank you. I'm happy to stay and take questions, arbitrarily many questions. Yes.
Is there a way that you could empirically distinguish from other formulations?
That is an excellent question. The claim is that none of the other formulations work.
Yeah.
So take, for example, the many worlds interpretation.
Mhm.
Elizabeth, it's good to see you. The many worlds interpretation only works if by fiat you declare that somehow out of non-probability, out of the theory that's just some deterministic, like universal wave function evolving, that magically probabilities can somehow come out of it.
Right.
No one is given an airtight argument for that's supposed to work. So I would argue that it's falsified at the gate,
Okay.
right? Until someone can explain in a rigorous way how you get probabilities out of a theory that has no probabilities.
Right.
And all the problems that bedevil attempts to get probabilities out of many worlds interpretation, I would just say that it's simply empirically inadequate. It's not another formulation. It's just not there. Bohmian mechanics has not successfully been generalized to arbitrary quantum systems, even to just like relativistic quantum systems, let alone relativistic quantum field theories. There have been attempts. They're very, very rudimentary, and they can't even predict the most basic things. There's a many-worlder, David Wallace, philosopher of physics, who's been giving a bunch of talks and wrote a paper called it's like quantum mechanics in the blue sky, like why the sky is blue. And his point is just that Bohmian mechanics, even after 70 years, is not yet able to account for why the sky is blue. Like it can't handle Rayleigh scattering, which is a very basic requirement. So if you look at the landscape of available quantum interpretations, I don't think any of them are sufficiently robust that I even know what they're even claiming comes out of experiments. Now, there are exceptions. Stochastic collapse theories do actually make robust claims. Stochastic collapse theories say there's the Schrodinger equation most of the time, but every once in a while there's this collapse event, and it occurs according to a very precise law. Those are absolutely empirically accessible, but they make predictions that are different from textbook quantum theory. And people are looking for those deviations.
Okay, that's cool. I didn't know that.
So this picture doesn't make the same predictions as stochastic collapse theories. And so if the stochastic collapse theories fail, if we don't confirm them, if they turn out to be empirically like not matching what we see, I don't know what else is really out there, to be honest. Just very rudimentary interpretations that aren't clear about what claims they make empirically. That said, this approach does not take wave function collapse to be a fundamental process. As you can see, it's just what things in the Hilbert space look like when classically you just condition on a measuring result, right? But without fundamental wave function collapse, you have what's called a no collapse formulation of quantum theory. Now, Everettian or many worlds quantum mechanics is a no collapse interpretation. Bohmian mechanics is a no collapse interpretation. The no collapse interpretations make subtly different predictions from the collapse interpretations. But the deviations are expected to be extremely difficult to determine. Because remember, collapse happens in a measurement. That means that a big macroscopic system with moles upon moles of degrees of freedom has interacted with the subject system. And if you take collapse to be a physical process, or take textbook quantum theory to say that collapses are happening only at measurements, right? You are altering unitary evolution. You're not getting exactly unitary evolution, but the deviations from unitary evolution are going to be so unbelievably small. They're going to be thermodynamically small. To give you a sense of what this means, suppose you could do the Schrodinger cat experiment. You know, the cat in the box, you all know the experiment. I have to tell you the experiment. You know the experiment. Radioactive atom, gas. Suppose you had the technology to do an interference experiment on the entire cat. Like take the cat that's alive and the cat that's dead in superposition and observe their interference effects and confirm that collapse had not truly occurred. There's a theorem, it's actually a very easy theorem to prove. Scott Aaronson proved it a couple of years ago, but like once you ask the question, proving it's not very hard. He calls it quantum necromancy. Necromancy is like magical incantations that bring the dead back to life. Because what he shows is that if you have a machine capable of detecting those interference effects between a live and dead cat, then with a very simple change to your apparatus, you can take a cat that is definitely dead and restore it back to full life. And I don't mean like mostly dead. I mean like all dead. Like you do the experiment, you wait hours, the cat is definitely very dead. And you bring it back to life. We think that bringing cats back to life after they've been dead for hours is thermodynamically difficult. But what that theorem shows is that it would be just as difficult to see interference in that experiment and show that wave function collapse had not in fact happened. So to the extent that no collapse interpretations and collapse interpretations don't make the same predictions, it is the level of effects that are expected to be unimaginably difficult to probe. Maybe not impossible, but not within our present realm of technology. And as far as I know, I can't think of any other definitive ways to distinguish between the two cases, but there are some speculative ways you might distinguish between them. Let's suppose that you want to predict the behavior of a gas of particles in a box. Now, what you're certainly not going to do is write down dynamical microphysical laws for the 20 moles of particles in the box. You're not going to do that. A mole, remember, is 6.02 times 10 to the 23, right? If you've got like 20 moles in the box, there's just not a computer that exists that's going to do it. Now, you also aren't usually interested in the individual trajectories of the particles anyway. You are only interested in gross behavior. But my point is that predictive behavior of this thing, you're just not going to be able to track all of them. You're not going to know all of their initial conditions. The dynamics is almost certainly chaotic. So you would require a completely unrealistic amount of precision in the initial conditions for each particle to predict what's going to happen. And you've got 6.02, so you're just not going to do it. So the question is, how do we make any predictions at all about a gas of particles in a box? I mean, we've got Newtonian mechanics. We're not using Newtonian mechanics. So how are we making any predictions about the box at all? How are we making all these claims about gases and boxes, the ideal gas law and adiabatic expansions and Carnot cycles and all that stuff? If we're not using Newtonian mechanics, how are we doing it? The answer is we're using these higher level laws, the laws of thermodynamics. And when anyone asks you where do those laws come from, people will say, well, they can be motivated or derived from Newtonian mechanics in some very simplified cases, and we think that they're ultimately they're so-called they supervene on Newtonian mechanics. They emerge from Newtonian mechanics, and once we have them, we can use them directly and then make the predictions. But it turns out that's not quite true. The laws of thermodynamics do not only emerge from Newtonian mechanics; they also emerge from auxiliary assumptions. What do I mean by auxiliary assumptions? There's a funny little anecdote in a book by the philosopher of physics David Hilbert that says there is nothing in Newtonian mechanics, nothing in the laws, nothing in the microphysical, ethical dynamic, nothing, that would say that a bunch of atoms, Newtonian atoms, dust particles, will not, in the next 10 minutes, fly together and assemble themselves into a collection of statuettes of the Roman emperors. You might go, that's impossible. Is it? I can certainly write down a Newtonian process in which that happens. So on what grounds do you say it's impossible? And what you'll say is, well, it's just very unlikely. What do you mean?
Stat mech.
What do you mean by stat mech?
As you say, it's very unlikely for particles to.
It's unlikely, but on what grounds? You can't just take Newton's laws and say it's unlikely. You need additional assumptions. And the assumption is that the initial state of your system has to be highly generic, highly typical, highly non-special. Not like any of you, you're all very special. But the initial conditions have to be very non-special, right? And if they're sufficiently non-special, then the likelihood of them assembling into, particles assembling into the Roman statuettes is negligibly small. But what do you mean by not special? Newton's laws don't talk about specialness or not specialness. What you have to do is you have to take all the possible initial states that could possibly exist. You have to put some kind of probability measure on them. And then you have to say, I'm going to add as an auxiliary assumption that the initial conditions are in one of the typical states according to that measure. That's not part of Newtonian mechanics. And without an auxiliary assumption like that, you can make no predictions at all about macroscopic statistical systems, none. And this is one of those deep problems with statistical mechanics that I mentioned at the end that many philosophers are worried about. How do those probabilities show up? Does God put a probability distribution on all the microstates? Like, what does that even mean? The universe only has one microstate. So what does it mean to say that there are many and then there's what does any of that mean? And you can get around some of those problems by having actual probabilities in your laws instead of relying on the initial conditions. But the point is that without those auxiliary assumptions, you can't make any predictions about statistical systems. This indivisible stochastic quantum this correspondence says that indivisible stochastic systems have the same microphysical laws as quantum mechanics does. But it says nothing about any of those auxiliary assumptions. And because we're replacing the Hilbert space as the state space with a configuration space, which is a different kind of space, and we're replacing unitary evolution with stochastic evolution, which is a different class of dynamics, it is almost certainly the case that we have to replace our auxiliary assumptions. When one does quantum statistical mechanics, when one studies, for example, how it is that quantum systems approach equilibrium unitarily, there's a whole bunch of theorems on this, there's many body locals, it's a whole area of research based on that's devoted to this. One puts probability measures down. One says which density matrices are the typical ones. One says which unitary evolutions are the typical ones. Usually the Haar measure is used for the unitaries, right? And some unitarily invariant measure is used for the density matrices. But we're taking all those spaces, the space of states, the space of dynamics, and we're replacing them with different spaces. With different spaces means different measures. And different measures, different definition of typicality. Different definition of typicality means possibly different auxiliary assumptions. Different auxiliary assumptions means possibly different predictions about the statistical behavior of these systems. So the claim is that if you have a quantum system that is thoroughly in the classical limit, right? So it's a big quantum system with lots of particles, but it is heavily monitored by its environment. It is behaving very classically. Well, then it's just going to obey basically the laws of classical statistical mechanics, and we know what will happen. A quantum system that's very, very, very small is not going to be treated statistically, and that's going to have the same predictions whether you're using indivisible stochastic process or not. But if you have a quantum system with a large number of degrees of freedom, so it's thermodynamic, it's statistical, but not classical yet. It's somehow a very, very many-body quantum system that needs to be treated statistically with auxiliary assumptions, but without the classical limit, then in principle, there could be deviations in the predictions for those systems because you change the auxiliary assumptions that you need to make predictions for exactly that class of systems. So that's one possible place you can look for deviations between this picture and textbook quantum mechanics.